Okay, so we are continuing our discussion. So the point we have left in the earlier lecture, I have this observation vector x, and I get my optimal estimate for the vector y using this relation. Ryx, this is the estimate, Rx inverse times x. Okay, this is the optimal estimator in linear MMSE sense. So somebody tells me that if I linearly combine this, or if I linearly map this vector to any other vector, let me call this x of m vector, do I get a better estimate? You can say that this will be, not very likely. Why do I say so? Because if I linearly combine the elements of this, then at the end there is a W weight. W weight is also linearly combine these elements. So at the end, this combination effect can be cancelled because there are two linear operations and one of them is invertible. But let me see this. If this second person, let's say processing the observations first with M and then applying this MMSE result, do you think the result will be different? So y hat, so this is R, y, xm, Rx, xm inverse x. Isn't it? Because it's the same result, the only difference is this. So how about this one? This is expected value of y, xm is m times x. M times x, but please remember there is Hermitian over here. How about this one? This is the inverse of a matrix, this term. Okay, so this is Rxm. We know that this is m, Rx times m Hermitian. Okay, so if I write them over here, so what do I have? So let me process this a little bit. So this is y, x Hermitian, m Hermitian. Okay, so this is R, yx, definition, m Hermitian. How about this one? Inverse of this. M Hermitian inverse, Rx inverse, M inverse. But sorry, I made a mistake at the beginning. This person is processing xm with this. So this is xm. xm is m times x. This is xm. The second person is using this as the input. Okay? Input of the estimator. And obviously, you can see that this m cancels. So we get the earlier result. So this is, let's say, the second person m's estimate. So this is nothing but this estimate. Okay. So we see that this does not affect anything. And indeed, this is not surprising, as I have said. Because please remember, this is not very surprising because the reason is this. Y hat is nothing but W Hermitian times M times X for this one, where Wm is calculated like that. So since I'm free to select this matrix, I can always affect this, I can always include the effect of this M in this W matrix and then, generate another weight, okay? So what I'm trying to say is, you cannot get a better estimator if you process your inputs linearly by this M matrix. Okay, that is one of the things. So is this thing totally, of any purpose, or can it be useful by processing, this pre-processing, let's say, my input vector x by M matrix? Can I get some useful result or not? That is the question. So let me write a brief note. This is a little bit more advanced than usual. So let me write recursive estimators. I will briefly discuss this. So let's assume that I have this n element observations. So this is n observations. Okay. Now I know how to combine these n observations. Let me write n over here like this. So this is xn. and I know how to estimate, let's say, this y quantity. Okay, so this right now is scalar. So this is desired, not a scalar random variable. Okay, so this is the same equation that we have studied, for some time. Now let's assume that I have another observation. So this becomes a longer vector. So x1 to xn is identically the same. I have n plus 1. So what should I do? Now should I, repeat the same calculation for n plus 1 dimensional vectors? Okay. Is there a better way of thinking about that? Well, how can I? Well, this vector space idea can be useful. What do I mean by that? Now, you have n vectors over here, x1 to xn, and this covers this plane, as you see. Now you have an n plus first vector, okay? So this is, if it is on this plane, then this projection result will not change because it is the same place. If this xn plus 1 belongs to the span of these black vectors, then xn plus 1, this observation won't be helpful for me. But xn plus 1 is not in the span, okay? So this dimension of this vector space increases with the n plus first observation. So how can I do this? Well, if I can generate, for example, this, if I can, this vector, n plus 1 dimensional vector, it has a component lying over here, and it has a component not in this span of the black vectors. So if I can, get this vector somehow, that is the vector, this vector will be the newly added dimension to my earlier space. Okay, so the n plus first dimension will be along this vector. Okay, so you may say this will be the orthogonal sum of these spaces, this space and the orthogonal sum of this vector orthogonal to the earlier space. So what am I trying to do is, okay, so there is some idea about that, but maybe you will be agreeing with me if I do this. So let me write this let me write this equation system over here. Okay, so what is this? This one, let me write my vectors as we did all the time. Okay, how about this? This is, again, x1, xn plus 1, xn, and I have y over here, right? So this is expected value of x1 times y. This is expected value of x1 square, expected value of x1, x2. So what's interesting is this. Now I have this n by n block, which is exactly this. So this is xn, this is xn. So this matrix is n by n part is exactly equal to this Rxn matrix, because it is the same. As you see, x times x omission, it is the same. So what is new is, now I have a new variable over here, and because of that I have some changes. I have some inclusion of a column and inclusion of a row in this matrix. Because of this, this is the matrix of inner products, as I have said. So I calculate all the inner products with these other x1, x2 with the xn plus 1. So the issue is this. Now, if n plus 1 times x1, this is x of n plus 1 times x2. Okay, so it goes like this. The last one is x of m plus 1 square. Okay, I have this. Well, of course, this is symmetric matrix, so this is appearing over here, this one is appearing over here, and so on. Well, what can I do? I have to invert this matrix, but I know the inverse of this matrix. So how about this? Now I am defining, a new x vector. This is an n plus 1 dimensional vector. x1, x2, xn. And this will be xn plus 1 minus alpha 1 x1, alpha 2 x2, alpha n xn. So I have a vector like that. So if I define my observation something like this, so do you think my estimator will be different? Well, it won't be different because I'm processing my observation by an invertible M matrix. So this is nothing but a linear combination of, so this last row is nothing but linear combination of the other ones. Okay? So this is just like, processing but this M matrix. So if I use this observation with hat at my original observation, so I have some freedom in the selection of these alphas. Okay. So clearly we see that xn plus 1 appears only once and nowhere else. So we see that this vector, actually it's a random variable, but in the abstract space, this vector, because of this, is independent of the other ones. Okay, xn plus 1 is appearing only once over here. Okay, so what should I do? So it would be very nice if these are equal to 0, right? If they're all equal to 0, well, this cannot be equal to 0, but then if all of these entries, except the one on the diagonal, is equal to 0, then it will be very easy to calculate the inverse of this matrix, because I have an n by n matrix, and this last row is nothing but a scalar equation, and this is the only thing that I don't know. The earlier equations, the first n equations, are already solved over here. Okay? So if I can make the last row or the last column entries of this equal to 0, you can say that you can make them 0 by processing using row eliminations, by row combination, column combination, etc. But I don't want to do it that way. Can I make this 0? So how about this? Well, I will, again, a basic idea. So I will try to estimate actually xn plus 1. From what? I will try to estimate xn plus 1 from this x vector. Let me write it like this. Using the elements of this vector, 1 to n, I'm trying to estimate xn plus 1. Can I do that? Of course, I can set my desired random variable as, in this problem, as xn plus 1. Okay? If I can set it that way. Then this will be the prediction of it. Remember, in this problem, desired random variable can be anything. Y can be anything. It can be x, it can be y, it can be z. Provided that I can calculate this cross correlation, I can get this estimation. Now my desired random variable is xn plus 1, the new observation. Okay? So actually this is then estimation error, isn't it? xn plus 1 minus xhat n plus 1 from, let's say, n-dimensional x vector. Let me write it like this. xn, it's better. Okay? Again, using this linear MMSE sense. So what's the purpose of this? Well, if I do that, what do I have? Now let me try to solve this problem. So I need to find this equation. R x hat W, let's say with this problem with this observation vector, W this is equal to R x hat and Y. Okay? So this is an n plus 1 dimensional problem. This is n plus 1, n plus 1 and y. Okay, so if I write this matrix one more time, this is an n plus 1 times n plus 1 dimensional matrix. I have this w vector, n plus 1 dimensional, and I have this vector also. So again, this n by, let me make this a square as much as I can. So this n by n part, there are no changes over here, is this matrix. Okay? So this is Rx n. That part is Rxn. This is this matrix. Okay? So the other parts. So about this one, this is now this E. But what is this E? There can be confusion. Let me write this Ex n plus 1 over here. E x n plus 1. So this is the prediction error for the xn plus 1, according to this, times x1. This is the prediction error of ex n plus 1 times x2. And I have many terms. This will be the prediction error of e x n plus 1 square. Okay. Similarly, I have this term, prediction error of x n plus 1 times the first observation. Again, what is going on? So remember, how do I write this Rx matrix? I write x1, x2, xn, and this is prediction error right now. xn plus 1, x1, xn, e, xn plus 1. Is this clear? Okay. So if I construct optimal estimator, if I select these alphas properly, according to linear minimum mean square error criterion, meaning that I get, projection of this xn plus 1 over here, let's say. Let me erase this. n plus 1 hat. Okay. Then this error is orthogonal to this. This is the orthogonality, right? So this will be equal to 0. This will be equal to 0. So all of these will be equal to 0. If I can do this. So how about this part? This part is x1 up to xn. There's a y. So this is Rxn and y. How about this? This is E, xn plus 1. So this is expected value of E, xn plus 1 and y. So what has happened? Now again we see a decoupling effect. So what do I mean by decoupling? First, n equations like this are solved by the first, without this n plus first equation. Then once I get the solution of that, I'm done. So this coefficient, let me write w, okay, let me write this vector. This is w vector in n plus 1, first one. This n plus 1 dimensional. Okay. Now, the remaining unknown is, so from the top part of this matrix equation system, I get these ones. And the remaining unknown can be solved by this, dividing this number by this. That is it. Okay. So from this, we see that w hat, n plus 1 vector, the top part, w hat, n plus 1 dimensional vector, the first n elements is nothing but this one, w of n, because it is the same equation system. So the top part of this matrix is exactly equal to this. Okay? And W hat n plus 1 is equal to of n plus 1, last unknown. So this is the unknown. This is equal to expected value of prediction error times y divided by, so this is expected value of x n plus 1. Okay? So if I call this just, for example, k, okay, then what do I have? I have this. Then my y hat is this w vector n plus 1 dimensional times x. Okay? But this is nothing but xn vector, and there is a new observation over here. There is an Hermitian. Okay. So what do I have? So the top part is process bit x of n plus, so the last one is just k times, but this is with hat, right? I'm using this vector with hat. Okay, so this is my new input. K times, this is my last element over here, xn plus 1. X, this is n plus 1 dimensional vector. It's last element. So let me write this basically, right, because it's more difficult. So this is E of x of n plus 1, prediction error. So this is then equal to, this is the estimate with n observations. Okay, because please remember that these are the optimal weights for the processing of first n observations. Okay, so I have that. Plus, there is a gain, k, times, there is prediction error, and prediction error is this, new observation minus the prediction value of this new observation according to this x of n vector. Okay, so this is n plus first. So as you see, you get a recursive estimator like this. So this is our earlier estimate. So earlier estimate is updated. Assume that your prediction is exactly equal to the observation. Then there is no update. Okay? Then, you know, yn plus 1 hat is equal to yn hat. So how about this one? This is a prediction error, as I have said. This is also called innovation. Innovation means what is new. What is new in this observation is observation minus its predicted value. You can think about it like that. And this is the basis of recursive estimators. And essentially this is the basis of Kalman filtering, why Kalman filtering can be implemented recursively. Okay, that is it. So as you see, this orthogonality concept may come into play at different places, as you see. Okay, very good. Okay, that's all I would like to say about this. So, okay. There is one last thing. This will be shorter. Actually, it's a very important concept, but it's a little bit more complicated than usual, but let's keep it in our record. Okay. So then, estimation of linear combination of desired random variables from, let's say, x. So again, I have to explain this. So let me say we are given this x vector, observation vector, and we have estimated y according to this. This is also a vector. Okay. This is our optimal estimator in terms of linear MMSE. This is right now a matrix. Okay. Now the issue is, assume that we want to estimate, let's say, z is equal to, let's say, n matrix times y. We want to, okay, estimate from this x vector, okay, by processing this x vector. So what should I do? So question is z hat m times this y hat. So this is n. N times y hat is a good estimator or not? Okay, that is the question. So, well, there is not much to do actually. Answer. Let me try to find this optimal estimator of this. So instead of y, I'm writing, as you see, z. Okay, so this is optimal linear minimum mean square error estimator. Error estimator. Okay. So how about this? This is the different part. So this is the expected value of mn times y x Hermitian. But this is nothing but, you can move this n out, n times r is this, okay, y x, okay. Let me write it over here, y and x. Because I have y x Hermitian over here, then I get n times r y x Rx inverse times x. But this is n times, okay. So indeed, is the optimal linear minimum mean square error estimator. Okay. So you don't need to solve the problem again. So if you know, let's say, estimates for y, and if you are interested in the estimates for z, where y and z are linked like that linearly, then process the earlier estimates by n, and you will get the result immediately. For example, this can be a scalar even. Maybe you are interested in not in y, but summation of all of these y's. Okay? Then this is nothing but a row vector of ones. Okay. Then this says that if you are interested in estimation for the summation of all of these y entries, estimate y vector and then sum their values. Estimate y vector, y hat, and sum this y hat elements. That is it. Okay. Again, this is not very surprising considering, this orthogonality concepts and so on. Okay, very good. So that's all we would like to cover.